All right, so today we are going to learn about the econometric assumption. And the first assumption that we are going to discuss is multicollinearity. So, what is the outline for this meeting? So, first, we are going to learn the nature of multicollinearity, and then is multicollinearity really a problem? And then what are its practical consequences? So how does one detect it after we know the consequences? And if we can detect it, what remedial measure can be taken to alleviate the problem of multicollinearity? Right. So before we get into multicollinearity, let's review the assumption of linear regression model. So we have in total 10 assumptions. If we are going to use OLS as our estimators for regression coefficient, and from 1 to 7, the expectation of error, and then the variance of X, covariance of error, and then whether the error has normal distributed, covariance between error and the um, regressors, fixed regression, and linearity parameters. All of these 7 assumptions about is about the specification of the model and about the disturbance or error term. And then the last 3, which is multicollinearity, whether the number of sample more than the parameter we are going to estimate, and also the variability in X and no outlier, it's more um, about the data. It's more about the assumption of the data. All right. So let's move on to what we are going to discuss this time. It's about multicollinearity. So by definition, the multicollinearity is due to the Regnar-Frisk 1934, which originally meant the existence of perfect or exact linear relationship among some of all explanatory variable of a regression model. So here we are not going to talk whether there is or there is no multicollinearity, but like how severe or like the a spectrum of multicollinearity that we have in our data set. And it's about the real whether there is linear relationship between the explanatory variable or not. So this is 2 types of multicollinearity. That is, what is it called? This is the extreme cases. We have perfect multicollinearity, and the other one is imperfect multicollinearity. So perfect multicollinearity means that there is an exact linear combination in our regression. So if we have this lambda 1 x1 plus lambda 2 x2 until lambda k xk, which means if there is this lambda here is non, like all of them, some of them has non-zero values, which means that we have linear relationship between some of the x's here. So there is a redundant explanatory variable, which means that maybe, let's say, lambda 1 is non-zero and lambda 2 is non-zero and other lambdas are 0, let's say that. And then which means that this one here, which is our x1 and x2, will have a linear relationship. So x1, because this one, lambda 1, x1 plus lambda 2, x2 are non-zero, which means that x1 will have linear correlation with x2 and vice versa, which means that both of them are redundant. So we cannot separate, if we include them into regression, we cannot separate the effect of x1 and x2. And then there's also the second case, which is imperfect multicollinearity. Sorry. So imperfect multicollinearity, which means that the variables are highly correlated, but not perfectly. So they are highly correlated, but not perfectly. What does this mean? Which means that if we have this function here, there is VI, which means that the stochastic error term. So they have correlation which are high but not perfect. Like the coefficient correlation is not 1, it's maybe like around 0.8 to 0.9, but they are strong. The correlation between them are strong. So this is what we call imperfect multicollinear. Okay, and then next is multicollinearity. So let's say we have, let's review the previous. So take a look at this equation here. So this is the general equation. If we have k regressors, and then if, let's say, lambda 2 is not equal to 0, and then which means that we have this one, x2i, which is mean this is we move lambda 2x2 into the other side of the equation, and then we divide all of this lambda with lambda 2. All right, so perfect mean that the x2 will be the exact function of other, which means that they have correlation coefficient equal to 1. And then imperfect means that x2 will have coefficient correlation less than 1, but they are strong. So let's say this one. So if we have this function, and then we have x3 equal to 5x2, which means that x3 here is a function of x2. Okay, so and then if we take a look at this one, this data set here, 10, 50, 15, 75, 18, 19, this will be, if you check the correlation between x2 and x3, they will have a coefficient correlation equal to 1, which means that they are perfect collinear. But if we add a random noise, the correlation coefficient might not be perfect, like 1, but let's say it's like 0.99, which if we like make a round value, it will be equal to 1. But it still be a imperfect high multicollinear case. Okay, so here we know that x2 is 1/5, or x3 is 5 times of x2. So they have a high correlation. So here, there's, when we talk about multicollinearity, we are not talking about whether there is or there is not multicollinearity in our data, but we are going to talk about the degree of collinearity. So the degree here, which means that there is level of this multicollinearity, whether they are strong, they are perfect, or they are weak multicollinearity. So this degree actually can be measured by the extent of the overlap shed area. If you think about in this graphical regression, so let's say we have y, our response variable. Let's say we assume that y here is affected by x2 and x3. If there is no overlap area between x2 and x3, in this case, they are indeed no multicollinear. And then another case, if we have a relatively lower, like low shed area like this. So let's say x2 and x3 has a little bit same value, like but they are not so high. So if we check the coefficient correlation between x2 and x3, maybe they're around 0.3 or 0.2, which means that they have low collinearity. And then this is moderate, and this is high, and this is very high. And then if they on top of each other, like in the same shared area, which means that they are perfectly correlated to each other. So which means we will have perfect multicollinearity. So that's what we are going to discuss today. However, we have to note here that multicollinearity only refers to linear relationships. So if there's other type of relationship like quadratic, cubical, etc., we cannot um, we cannot measure them by multicollinearity. So it doesn't rule out the nonlinear relationship. All right, and then so this note here mean that let's say we have x. So in the regressor, we said that the variable that affecting y is not only x but also x squared and x power of 3. You know that x squared calculated from x and then you times its value, so we get x squared and then we times them with x again, we got x power of 3. They comes from the same variable, right? X squared and then x power of 3, but they're not linear relationship. They don't have linear relationship. Therefore, we cannot say we can say that they are not violating the multicollinearity. But still, it will in practice it will give you a problem because of the correlation between x and x squared. Right. Okay, so let's move on to the next slide. So this is the consequences of multicollinearity. So if we have perfect multicollinearity, mean that the regression coefficient are indeterminate, which means that your standard error will be so high, and then it will be hard to determine whether this variable is really significant or not, whether if they're not significant, can we believe that has so that what the consequences of multicollinearity. And then the other one is imperfect multicollinearity. So the coefficient are determinable. We can determine the coefficient, but we will have a very large standard error. And then our estimate will be unreliable, which means that we cannot trust the test, the ANOVA test, the partial test, and the F test of our regression coefficient, because the standard error will be inflated, and then of course it will affecting whether those variable are significant or not. And then there are several causes of multicollinearity. The first one is data collection method. So let's say we get a sample over a narrow range of value, it will introduce multicollinearity. So it doesn't represent the whole population. Let's say survey of income that exclude the extreme value. So we will have less variability in our eggs, mean that it might have a multicollinearity. And the second source be constraint in the model or population. It can be physical, it can be logical constraint that cause correlation. So let's say we have X is income, so the regressor's income, and then the other is house size. We know that they're naturally correlated. So we can say if people have high income, will most likely have a bigger house, or people who have low income most likely will have smaller house. So because naturally they are correlated in the population, it will introduce multicollinearity. So be careful when selecting variable in your regression. And there's the third one could be from model specification. So let's say we include the polynomial term like what I explained earlier. So like x, we also include x squared in the model. In that case, it will obviously will have a correlation, or any other function, any other variable that actually functionally related. Like the previous example, when we say x2 is sorry, x3 equal to 5x2, which means that x3 is functionally a function correlated from x2. So that's one of the resource of multicorrelation. Sorry, multicollinearity. And it's actually common in medical or biological study with limited sample, but sorry. The fourth one is overdetermined model. So this one common in medical and biological study. So usually, let's say we are going to study about the the composition of some gene in our body, the gene, and then we want to predict the some disease based on the characteristic of the gene. Usually, we will have a lot of predictors or a lot of regressors there, but the sample will be less than the number of predictors. That's why it will be overdetermined. And then the last source could be from common trend in time series. So usually some variable who like they move in the same patterns together over time. So let's say income, population, and consumption. As the income increase, as the population increase, the consumption also increasing. So because they increase together, they move in the same patterns, like same, they have same trends. It will cause collinearity, which will lead to multicollinearity. And then this is the estimation in the presence of perfect multicollinearity. So to introduce the effect of multicollinearity, I will show you this mathematical illustration. So because earlier in the slide, I said that in perfect multicollinearity, regression coefficients are indeterminate, so we cannot determine the coefficient, and then standard error will become infinite. So this problem only arises when variables are perfectly collinear, which means that they have coefficient correlation of 1. So let's say this one. We have a regression model, like this one, yi equal to this one, and then we assume that x3 equal to lambda x2, and then if we calculate the using OLS, beta 2 will be equal to this one here. And then because x3 equal to lambda x2, and then we substitute x3 here into lambda x2, they will have this final result, which means that 0 over 0 will be indeterminate. So we cannot find the value of beta 2 hat because of this relationship here. You can prove by yourself by substituting the x2 here with this one. Oh, sorry, we substitute the x3 with lambda x2. So every x3 here, you change it to lambda x2, this one also, and this one too, and this one too. And it will lead you to this final result, which means that we will have indeterminate results. Same as beta 3. You can check by yourself. So that's the consequence of multicollinearity, if they are perfect multicollinearity. So actually, especially in econometrics, we want to have the partial effect. So we want to know the effect of x1 we want to check the effect of x2 holding x3 constant, and then vice versa. We want to know the change in y per unit, change in x3 holding x2 constant. So we want to estimate the partial effect. So under perfect multicollinearity, this goal will be failed. So because we cannot isolate the effect, or we cannot separate the effect of x2 and x3, there's no way to separate their influence like that, because we know that beta 3 has effect on beta 2, vice versa. So there's no unit value for beta 2 and beta 3 because they are from the linear combination of them. That's lead to identifiability problem in the model. And then the next one is, how about they're not perfect but high multicollinearity? So we often face this problem. So they have high correlation but not perfect. So this is especially common in economic time series data. So let's say the OLS estimator will be look like this. So you just need to change the you can check in your textbook. So we will have this one. So we know that x3 in the imperfect multicollinearity, we know that x3 equal to lambda x2 plus any random variable. So we'll write here. Oh, sorry. I think it will be slow. All right. So let's say x3 equal to lambda x2 plus vi, because we know those linear function, and you substitute any x3 here with that one, with lambda x2 plus vi, and then this actually any x3 you change it into that one. So here you will have a large estimation, but we will have finite variance, which means that if the collinearity becomes too strong, the estimation here will be unstable because the variance will be large, like that. So that's why by theory, the consequences of multicollinearity will be this one. Even with high multicollinearity, OLS will still have blue estimate, which means unbiased, consistent, and efficient. But because of the multicollinearity, the standard error of your estimation will be inflated. And then because of the standard error becomes so high, it will be hard to detect the significant difference or whether they are statistically significant or not. And then it could be because of that, um, it will be severe, like the consequences will be worse if you also have small sample size, which means that if you have multicollinearity and also you have small sample size, the variance of your estimation will be larger, and then your standard error will be also larger, which means that it will be hard for you to decide whether this is significantly correct or not. So what should you do if you have multicollinearity, and what if you do if you have few observation? So this is the difference between what is it called multicollinearity and then small sample size problem. So they will give you the same problem, which means inflated the variance, but it's hard. You have to detect whether the inflation of variance in your estimator due to multicollinearity or due to the small sample sizes. So this is the example of multicollinearity. Let's say if we have this regression model, consumption equal to beta 1 plus beta 2 income plus beta 3 wealth. Uh, Ideally, to assess the individual effect of wealth and income on the consumption expenditure. So ideally, we need a large number of sample observation, or maybe like sufficient number of sample observation of wealthy individual with low income and high income individual with low wealth. But we know the fact that there is not true. So because the income and the wealth are always linear, people who have high income will be wealthy, and people will that have low income will will have low wealth whatsoever, because uh because of that correlation, it will be hard to separate the effect of income, whether um the consumption is due to the income or the consumption due to the wealth, or we cannot separate the effect of income with to consumption with wealth to consumption. It will be hard. And then, so in this case, we will need a larger or more diverse sample to address this problem. So we will need that one, the wealthy individual with low income and high individual with low wealth, which means that it might be hard to find that because the nature of the variable itself, it's not like that. All right, so when multicollinearity is high or near, it creates practical issue even though OLS estimators remains blue. So this is the first consequences, which is large variance. So OLS coefficient can have large variance and covariance, which makes the estimation is less precise. And then the second consequences is wide confidence interval. So because of variance, it's related to the confidence intervals. The confidence interval become wider, and then it leads to accepting the null hypothesis more easily, even though they're not. Let's say we are supposed to reject the null hypothesis because the um, confidence interval is wider now. It will lead to us accepting the null hypothesis easily. So we will fail to detect the significant predictor whatsoever. And then the third consequences is insignificant t value, because we know that t value is calculated from beta hat per the standard error of beta hat. So if the standard error is large, the t value automatically will be small. So the coefficient becomes statistically insignificant even if like in fact they are actually important, but because of this multicollinearity they might become insignificant due to the inflation of standard error of your coefficient. And then the last one is high R square but low significant. So actually, if the model is correct, if you have high R square, like which means that your model have a good variability, a good portion to capture the variability of the data set. If you have high R square, but then when you take a look at the partial tests, none of them are significant, which means that there's something wrong with your model. There might be a multicollinearity, because multicollinearity actually can inflate the R square. So model will seems fit well with your variability in your dataset globally, but when individual predictor are tested, they are insignificant. They're not statistically significant. So it will lead to incorrect interpretation. And the last one is sensitive to small changes because of the high variance. So the coefficient and standard error can be unstable. So let's say you only change a small portion of your data, it might give you a big changes in the coefficient estimate. So that indicate the non-robustness of your model, or your model will be fragile to any small changes. All right, so let's talk about one by one the consequences, the technical details of the consequences of multicollinearity on your OLS estimators. So let's say we have this one. This is the formula of variance of beta 2 and variance beta 3, and then also the covariance. There is R, there is R to 3. So R to 3 here is correlation between X2 and X3. So if we take a look at this, as R to 3 is equal to 1, this one here will be 1 minus 1, which means that it will be 0. So any value divided by 0 will be infinite. So therefore, here the covariance will be infinite. Here, this is the first consequences. And then actually there is a matrix that you can use to measure this one. It's called VIF, variance inflation factor. So we can measure whether this correlation have multicollinearity or not by calculating the VIF value. So it's calculated by 1 per 1 minus the R square of this one, R to 3 square. So this VIF value here will measure how much variance is inflated due to multicollinearity. If it's small, which means that we don't have multicollinearity, so VIF will be equal to 1. And then if we have high VIF, which means that your variance is inflated, and then your coefficient estimate will be less precise. So let's take a look at this illustration here. So let's say this is the covariance of beta 3 and beta 2, or we can say the correlation coefficient of x2 and x3. If they have around 0.8, the VIF will be 2.78. And if it's the coefficient correlation equal to 0.90, the VIF will be equal to 5. And if it's the correlation, if 0.95, the VIF increased significantly to 10.26. So, and then even if you add the only 0.02, the coefficient correlation, if the coefficient correlation only increase by 0.02, the VIF here is significantly becomes larger and larger. So just a small increase in correlation will give you a huge jump in VIF. That's why near perfect collinearity will cause instability. So the second consequences is wider confidence interval. So you can say here, because of as multicollinearity increase, your standard error will be bigger or larger, because the formula how to calculate standard confidence interval comes from standard error. We can say as the standard errors grow, the confidence interval becomes wider. So we will have a less lot of precision. So it will increase the type 2 error, which means that we increase the probability of failing to reject the false null, and it will give you a weak statistical power. And then the next consequence is sensitivity of OLS estimator and micronumerosity. So even with imperfect multicollinearity, actually OLS can be highly sensitive to even slight changes in your data. Let's say here I will swap the row of x3 and in the third and the fourth row, I will swap the value. And then let's see how coefficient change. In this first data set, the original one, the beta is 0.08, and then it's significantly significantly have a significant effect to y. And then if we swap the row here, we can say that the coefficient is 0.12. It changes, but if we take one decimal point, it will be the same. However, the statistical test changes drastically. So small change in your data will have a large change in beta coefficient and then the standard error and eventually to your statistic test. So usually you can have this problem here. As you can see here, even though and then also the R square here is still the same, but here they are significant, and in this case, they are not significant. So that's the problem here. This is some illustration example here. So let us consider consumption income example. So let's say consumption data is affected by income and wealth. And then if we assume that consumption expenditure is linearly related to income and wealth, we will have this regression here. If you can see here, the R square is pretty high, like 0.9365. It's pretty high. It's almost 100% R square. However, if you take a look at the t-table here, t-test, both of variable x2 and x3, they are not significant, which means that there is some problem. Why the R square is high, but none of the variables are significant. So that's the problem. Now let's take a look at the F table here. If we look at the ANOVA, the F test, which means the to test whether the model is true or not, it has a high F value, which means that obviously the model is significant. But if you take a look at the individual effect, they are not significant. So that's the consequences of your multicollinear case. And then it's also, you can look at this phenomena as a sign with this is a sign that there might be a multicollinearity in your case, something like that. So then it will be impossible to isolate the individual impact of your model. So as a matter of fact, if you regress x3 on x2, so we regress the regressor, one of the regression to the other of regressors, we can see here that they are significantly affecting the x3. x2 has a significant effect to x3, and the R square is also high. So now let's choose one of the variable. So we don't both x2 and x3 to the regression model, but we will choose one of them. Let's say we choose x2 to y. We can see here the R square is still high. And then now x2 becomes significant to y. And then also, if you choose another variable, x3, the R square is still high, and then they are significant. So it's better to choose one of the variable if those variables are highly correlated. So how we detect the multicollinearity? First, from this example, we can say that if you find high R square but low T ratio, it might be a sign of multicollinearity cases. And then you can check the pairwise correlation between the X or between the regressor. If they have a high correlation, let's say the absolute value of error regression, sorry, correlation coefficient is more than 0.8, it may indicate multicollinearity. So if you have some of the variable have high correlated, maybe it's wise to choose one of the variable and not including all the variable. But this is not a necessary condition. So sometimes, even though they have a low correlation between the regressor, collinearity can still exist. So then how do we check? Let's say this one. So let's say this example, if we have this regression, y equal to this one, x2, x3, x4, and then we know that x4 here is linear function of x2 and x3. And then if the correlation coefficient of x4 and x2 equal to 0.5, x4 and x3 equal to 0.5, x2 and x3 is minus 0.5, and then the R square of this one, the R square of this regression here is equal to 1. Even though the pairwise correlation here is pretty low, but when we do regress x4 to x2 and x3, the coefficient determination of R square is equal to 1, which means that they might be have a high correlation in this case. All right, and then the next one is partial correlation examination. So this is suggested by a researcher, one of the researcher, Farrar and Gruber. So if you do partial correlation between the variable, so let's say if R square is high, but partial correlation is low, which means that the collinearity is likely and it might not be reliable in complex or small sample. So this is the definition of partial correlation. So let's say if we have variable x and then we have variable y and there's another variability z, and then the x and the y is correlated through z, this is what we call partial correlation. Yeah, I think you should learn this in the basic statistic classes. And then we can check the auxiliary regression and f-test. So here, if you regress the x on the remaining x, which means that you regress one of the regression to the remaining regressors, and then you calculate the f-test, if they're significant, which means that the x is collinear with other variable. Or you can see the R square of that test. And then based on that, we can also calculate this one, VIF. So RJ here will be the R square that you get from this auxiliary regression. Okay, so this is the rule of thumb. So because in previous table, we know that sometimes these changes on R square give you a high jump on VIF, but some people say that VIF greater than 10 can indicate whether they have multicollinearity or not. But there is a general VIF threshold based on several studies. So this is the general cases. So because multicollinearity is not about whether there is or there is not multicollinearity, but it's more about the level of multicollinearity, we can make this threshold. So if PIF equal to 1, there's no multicollinearity. If there is the VIF between 1 to 5, we will have moderate correlation, but still acceptable in some cases. But if your VIF value between 5 to 10, it will have a potential problem. And you need to take a closer look whether it will disrupt your interpretation or not. And then if VIF greater than 10, it will have a serious multicollinearity. So this is the reference that using different VIF value, so you can check and take a look closer to that. And then another way to detect multicollinearity is by the scatter plot metric. So this is similar to the pairwise relationship. You can add the visual inspection also. So what do we do next after we know how to detect the multicollinearity? The first thing, the first option is do nothing. So we accept the multicollinearity as the data feature. So multicollinearity often reflect the data deficiency. Let's say we don't have enough resource to get a lot of data. So there's nothing we can do about it. And we may not have control over the sample. So even if we can estimate beta 2 or beta 3 precisely, we may estimate the combination of them, like alpha equal to beta 2 plus lambda beta 3, or we can use practical solution to reduce the impact. And then the second option that we can have is use a priori information. So let's say if we consider the model here, so the same, if we know the theory that tell us this one, so this is a priori information. There is a theory said that wealth equal to 0.1 of income. And then in that case, if we know this theory, we can separate, it will be useful to separate x2 and x3, and we can simplify the model into like this. So using mathematical equation, we can use this economic theory to simplify our model. Or another option, we can do combination cross-sectional and time series data, which means that we will use pooling data. So we'll combine stable cross-section data with trending time series data and use one to control for another. So let's say we control for income from cross-section and then regress on time series of price. So, but however, here it might create problem of interpretation, because here we are assuming implicitly that the cross-section estimate income elasticity is the same thing as that which would be obtained from the pure time series analysis. So this is what you have to take a note and pay attention. And then the last one is dropping a variable. This is the simplest way to do. So we drop, so this is the simplest fix that you might do. And then, however, if you drop some variable, it might introduce specification bias. So there's not one fits for all solution here. So there is a sacrifice, like you sacrifice something to mitigate something. So that's what it is about. So we can use this remedial measure when the variable is not essential for interpretation. So we can use any variable that sounds less important from the other and choose the one that is more important into the model. However, uh, if both of the variable is actually important to the interpretation, it might dropping one of them might introduce a specification bias in your model. And then the last, not the last one, the other solution is first different. You calculate the first difference using like the concept of first difference in time series. Um, it will remove trends that cause correlation between variable. However, it might lead to serial correlation, or even we gonna lose one of the degree of freedom, and also we introduce the heteroscedasticity here. So this is the consequences of doing first difference transformation. So, and then we can another solution, we can add additional or new data set to add more variability in our sample. So when we have larger sample, the variance will be increased, which means that the standard error will be decreased. And then we can reduce collinearity in polynomial regression. So multicollinearity in polynomial regression, we can be caused by this one, the involved of x and x squared and x power of 3. We can use division form, like subtract the means, or we can use orthogonal polynomial too, like factor analysis or PCA, or even we can use rich regression too to reduce the dimensionality of our dataset. The question is multicollinearity is always bad? But it depends. If the goal is prediction, you can examine the R square. So if you have high R square, which means that you have a good fit, which means that the predictive accuracy might be still high. However, multicollinearity might not matter much if your prediction value are within the same structure as the original sample, and the linear relationship among variable remain consistent. But you have to be careful if the objective of your analysis include parameter interpretation, reliability of coefficient estimates, then the multicollinearity case becomes a serious problem because it will inflate the standard error, reduce the significance of estimates, and makes inference will be unreliable. So when it's not a serious problem, even if the R square is high and coefficients are statistically significant, the effect must still show up clearly because coefficients are numerically large enough to remain significant. So the true effect size is substantial even with the large standard error. All right, so that's all for the multicollinearity cases. Please take a look at Montgomery book exercise 10.27 and also 10.1, 10.8, 10.12, and so on as your homework. And that's all for today.